Hello, this is Anna from Chef. In this video, I'm gonna show you how to use the Atoms physics solver to simulate a rigid body in Houdini. Okay, I have already prepared a simple scene here with some rigid body. So I have, let me hide this one, a simple box and a torus where I create some fracture and I create some path geo to be able to use in network constraints later. So let's hide this guy for a moment, dive inside the top network. To simulate with Physx, you need to use the atom solver and you need to enable dynamic here. It's like the solver in Maya. And you can use the standard rigid body object to import a normal rigid body object. You can use the same parameter here, initial state, the physical state. If you need custom attribute for Physx, you need to apply some other data. So you can create an apply data node, and then an Atoms Physx data node. This node contains all the specific physical attributes for a rigid body. So you can choose the mesh type. You can set up for the damping, and here are parameters for different mesh type, cutout, offset, and other option. You can use packet geo as well, so you can just import like a normal RPD packet object in Houdini. And let's disable the constraint for a second, and then let's play. If you want to create some normal constraint, you can do that using an Atoms constraint node. Here, for example, let's put two. I want this one. Let's move a little bit the constraints here. And then let's change some attributes. Let's switch to D6 constraint. All those attributes are the same that you find in Maya. So you have all the projection, breakable option, limits for all the standard type. And here for D6, you have different options for angular, linear, and here you find all the limits attributes. So if I press play, it's a normal join constraint here. So now let's have a look to the constraint network. So the setup is the same that you use with Bullet. So you have a constraint network that is referencing a subnode that contains all the connection between each different pieces. Right now it supports only Spring constraint with constraint network. In the future we'll support also like pin and proper Physx constraints. Then you can use also subsolver here as well, just normal constraint network. But let's have a look a bit on the setup of these constraints. So in this example, I'm using Voronoi nodes to fracture my object. Then I have the assembly here that go to the packet object. For the constraints, you need to take care two things. So one is the standard one, so you need to like set up the constraint name and type. And for now, I just support Spring. But you need to pay attention the namings of the data that come inside the DOP network. So usually, basically, if I check the contents, jump to contents here, some node in Houdini just generate like piece 0 and 1 without this prefix, but you need to have a prefix like the name of your rigid body object in DOP. So for example, in the DOP, I have my packet, and I'm using this object name. So you need to have a name with that prefix on each primitive here. For this reason, I put this Ragdoll to change the name in a torus piece, because if I turn off this guy here, write just piece. Okay, so this setup, just go here and set the path to the constraint, activate, and then press play. Let's have a look at this scene where I stop some Ragdoll on some soldiers and some arrows here. So the simulation is like this. So let's have a look. First start with the soldier. So the soldier is using grid layout state machine and attach a Ragdoll module. Let's have a look at the Ragdoll module. So the Ragdoll module has a mode attribute. This one defines the Ragdoll mode that the agent is using. So at the start of the simulation, the agent starts with a kinematic. So it means that it's using the input animation from the crowd simulation. And then there is this on dynamic on collision. The Ragdoll operator turns the agent in a motor Ragdoll when there is a collision between the agent and some other rigid body in the scene. And then I enable the breakable. In this case, I set up the breakable on the shield and the sword joint, and I set up that here. So basically this one is a filter on the joint name. It means that it turns as breakable the joints, the sword shield and the sword joint and the shield joint. Then there is also this dynamic on collision filter. It means that the operator will not switch to the motor Ragdoll mode when some rigid body will collide with the shield. And in this case, there is an example, some guy like here. So you can see the arrows got stuck on the shield, but it's not turning the motor Ragdoll mode here. And then at the end, I have some other parameter, like the damping or stiffness of the motor Ragdoll and the max force. And there are all other attributes that you can find the documentation online, or they are the same attribute that you can find also in Maya as well. Now let's have a look to the arrows. So the arrows are using a arrow meter and a Ragdoll operate module as well. So here is a little bit different. So if you see, there is the mode in kinematic, but the arrow meter has a special mode that when it's used with a Ragdoll mode, then it will switch the arrows to rigid body to Ragdoll mode when basically it starts to simulate the arrow trajectory. So in this case, at this point now, there are already Ragdoll. And I put some attribute here, so you need to turn on the use dynamic mode metadata, because the arrow emitter module is setting metadata on the agents that will drive the dynamic mode here, instead using this attribute. And then I turn on to stuck on collision. It means that when the arrow got stuck with the soldier, it creates a constraint between them, so you have an arrow that remain in the hit position here like this. And then this one, there's a multiplying on the impulse at the contact. So for example, here I have some impulse, but if I multiply, for example, for 10 to exaggerate the effects, you can like multiply the force. Yeah, in this case, it's too much. Probably too much. So let's switch to 5 to be funny. Last thing, obviously you need to remember to turn on the enable dynamic option on the solver. Also, if you need to increase the substeps, also the scene scale. Here I set 100 because my agent is in centimeter. So it's for 1 unit, it's 1 centimeter in this case. So it's 100. If your unit is 1 meter, then you can leave 1 here. So for the last thing, let's have a look at the interaction between the Atoms, Ragdoll, and the other Houdini solvers. Let's have a look to the scene where there is it's an example of mutual interaction between multi-solver. So I have 2 agents. They are turning in a Ragdoll before follow in these fluids here. So I have an agent group here with grid layout, scene machine, and Ragdoll module. I put some keyframe here to switch to Ragdoll, exactly here, from kinematic, and then to Ragdoll. By default, if you don't change anything, you can have some interaction between some of the solver, but not the full interaction. So to be able to have the crowd fully interact with other solver, you need to change 2 things in the DOP network. So if you go in the DOP network in the Atoms agent group here, so you have these 2 options: the generate feedback object and the packet object. So the generate feedback object generate a Houdini packet geo for your crowd, and in this way Houdini can solve the physics based on this geometry, so your crowd can interact with other fluid, other solver. In this case I have a flip solver. If I press play, you see that the fluids interact with the crowd. And then the second, if you need mutual interaction, so if you want that the fluids apply some force on the crowd, you need to basically change the collider label. By default is known. That if you leave known, you can't use in this case the feedback scale. So if you leave that known and put this one to 100, you will see no difference. To be able to see the real simulation and see proper feedback from the fluid to the crowd, you need to switch to packet objects. This way the flip solver know that this crowd object here is a packet geo, and then it can apply feedback data on top. And when the Atom solver sees some feedback data on this geometry, then it applies that force and impulse to the crowd simulation.